Hello, Michela.
Oh, hi. Let me turn the video on. Oh,
Hi.
Yeah.
Thank you for the invitation.
Well, thank you for speaking. Are you Tsinghua?
Yes, I'm in Tsinghua. Yes, for several years now. And how are you?
Oh, fine. Yeah, I wanted to contact Tian.
Yes. Yes, I see him very often, like every week.
Yeah, because I think we have many ideas for potential collaboration. Both busy with other things. Oh wait, actually, let me make you wait, how do I make you? Awesome. Hi. You cannot make your co-host. Nicole?
Hey, Nicole.
Nicole,
hi. Hi, Mike. How are you?
Maybe I did something wrong. Maybe I logged in first from in the wrong way, and now I cannot.
You can make us co-host.
Let me try to log out. Let me try to log out and then log in from that other. But I guess, yeah, because otherwise I cannot make you co-host. Okay, yeah, let me do that. Okay.
We're all here.
Sorry. Okay, I'll do it now.
Thanks for doing this. Sorry that it's so early for you, I guess. Yeah.
It's okay. Thanks for the invitation.
Yeah, now I can. Let me make Nicole a host.
Okay.
Let's see if you can. Are you gonna use a tablet?
Yes, I will try to share.
Yeah, let's test that. Raphael, hi.
Hi.
Hi, Raphael.
Hi, thanks for the link.
Yeah, sorry I sent it till last minute. It occurred to me that
No. I was
not on the
just,
list. Yeah, I'm sorry.
I was just thinking, oh yeah, I forgot to, but no worries. That's perfect timing.
Good.
I started screen sharing, but I cannot see what I'm sharing.
We can see your desktop. We can see.
Okay. Wait, just a minute. I think I'm sharing the.
Oh man.
Right, I think I'm sharing. Just a minute. What happened? Okay, I'll try a different way. Okay. So do you see it well like this?
I see it. It works perfectly.
Okay. So the characters are large enough.
I think so.
Yeah, you can see them. Olaf, hi.
Hi, Misha.
Well, let's wait a couple more minutes.
Hi.
Hi, Monica.
Hi, good to see you.
Good to see you too.
Monica.
Hi. So Peng, what time is it where you are?
Oh, it's 8 a.m.
Oh my goodness, so early.
It's all right.
Hi, Michael.
Hi, hi.
Yeah, it's late, kind of late for you guys. It's a pretty good time for California.
Yeah, yeah. Oh, yes, yeah, for California, it's fine.
Yeah, kind of an inconvenient time for everybody else, I guess.
Yeah, the worst part is when we were organizing this, I was like, oh yeah, this time works great for me. I'm in Berkeley, it works wonders, but I'm currently in Boston. And
Oh,
so
no.
like totally like I think none of the
yeah.
organizers ended up benefited by this time slot.
I guess Australia, it might be a really good time right now. It's kind of early in the day there, I think.
It's like 3 hours late than us, so it should be something like 11 maybe or 10.
Yeah, but it's Saturday for you guys too, right?
It's Saturday, yes.
Yeah. What a great way to spend the weekend.
So perhaps we should start.
Okay.
It's a pleasure to welcome Peng Shan from Tsinghua University, and she'll tell us about coherent codification of quantum loop SL2. Take it away.
Thank you for the invitation, and thank you for making this special arrangement for time. So yeah, and thanks to Raphael for explaining some related things in the previous talk. So today I want to explain attempt to understand categorification of quantum loop algebras. So so let's start from a quiver Q with vertices at I and arrows at H. And as usual, we assume it does not contain edge loop. And so as we know, to such data, you can associate a Kac-Moody algebra GQ. And then like we've been discussing things about categorification of quantum groups associated to positive part of this E algebra. Okay, maybe just let me recap things related to this. So just a moment, I'll change. Okay. Right. So so Lucic has a geometric way to categorify UQ of n, and what he considers, you take you consider representation of this quiver. So for a given dimension vector, let's say beta, which is just you attach an integer to each vertices, then we can consider, so X beta is the space of representation of this quiver of dimension beta, which I assume everyone is familiar with. And then, so this is just a vector space, and it has a action of the group G beta by conjugation. Which, and then where beta I is just the integer attached to the vertices I. And then, yes, so you can consider the stack, which is X beta mod G beta. And then you have a convolution product which give you a monoidal structure on the category of constructible sheaves on this stack. So which is the same as considering G beta equivariant constructible sheaves on X beta. And then Lustig defined some subcategory here, which I think Raphael defined last time. So this is just a additive subcategory generated by some semi-simple complexes. So so which we can say is just generated by some intersection cohomology complex on this X beta, and then it's additive subcategory, and it's like stable under the shift of the derived category. Okay. Or maybe maybe better, let me just write this Lustig sheaf. So yeah, so I have a L nu for each nu which is sequence in I, and such that the coordinate of nu when you sum it up, it equals to beta. Okay. So so L nu is just the product. L nu is just the product of like the constant sheaf on nu1 with nu2. Yeah. Okay, so nu is a sequence in I such that the sum of nu I is beta. Okay. And please let me know if I'm not clear or if there's any questions. And then if I take this, I also need to take a direct summand to define this this additive category. Okay. So so then the theorem is that if you consider the split Grothendieck group of this category, it's isomorphic to the Lustig integral form of this NQ. And then where the shift corresponds to Q, and the induction corresponds to the multiplication here, and then the IC complex corresponds to canonical basis. So this is actually how Lustig defined canonical basis at the first place. And then as we know now we can understand this category in an algebraic way, which is provided by quiver Hecke algebras or KLR algebras. Oops, sorry. Due to Cohen-Lauda and Rouvier. And then, so that is to this quiver and some additional data you can attach. So you have a family of Z-graded algebras, which I will denote by R beta. So this is quiver Hecke algebra. And I think I will not write down the definition. It's, I guess everyone knows the definition. It's defined by generator and relations. And so this is Z-graded. And then what is important here is we now have this theorem by Rouvier and Varagnolo, Vasserot, which says that this R beta is isomorphic to the extension algebra of of all this sum of this Lussick sheaf. Okay. So in other words, this is a generator of this additive category. And this algebra describes the endomorphism of this generator. And so therefore you have it's like you give this algebra provides an algebraic description of this category, which was initially defined geometrically. And also you can recover from this that now, since now you have a functor from this category C beta, Cx beta to projective modules over R beta, like graded projective modules, and which is just provided by taking extension of this Lussick sheaf. And this is actually an equivalence of additive categories. And therefore you get an isomorphism of Grothendieck rings from here to here, and where now this shift in the triangulated corresponds to the grading shift. And this convolution, this induction defined by convolution now corresponds just to induce of algebras. You have, if you have R beta and R gamma, you can embed it naturally inside beta, R beta plus gamma. And so it corresponds to this. And then the IC complex just corresponds to self-dual indecomposable projectives. Okay. Okay. Right. So this algebraic description has many advantages, as we have seen in the development in recent 10 years. So in particular, you can also consider, so in this term, you also get a categorification of the dual form. So here on the quantum group side, you have a pairing over the field Q of Q, and then defined by Lussick, and then you can consider its dual form. So maybe just let me write here AQ of NQ, and then and then so you will see that on the quiver Hecke algebra side, this, like we know from this from initial work. So this is just the Grothendieck group. This is the categorification of this dual form is provided by finite dimensional modules over quiver Hecke algebra, graded, of course. Okay, and then so this is isomorphic to this, and then you have a dual pairing. Like here you have the pairing which is provided by the linear form. So provides a pairing, and here is just categorized by the home pairing between the projectives and finite dimensional modules, and maybe composed with the duality at the appropriate place. Okay, and then in some sense, in this category, you have more flexible, and it's easier to consider subcategories categorifying some subalgebras here, as I will explain later. Okay, right. And now the question we want to address is the following. So, so there's another perspective which comes from K-theoretical Hall algebras, which tells you that certain coherent sheaf, a certain category of coherent sheaf provides a categorification of the loop algebra of N. So, so this is the next part. Maybe let me just give the theorem right away, and then I'll explain the notations. So this is due to Varagnolo and Vasserot in the most recent preprint. So what it says is like now consider, assume Q is a finite type to simplify. I think they also deal with affine type, but here we're only interested in finite type. And then, so this quiver is of finite type, and then you can consider the following category. You can consider a certain derived category of DG coherent sheaves on the cotangent stack of this this x beta defined before. So we had this stack x beta was just the representation stack for Q, and now you take its cotangent stack, and there's a slight modification I'll explain later. And if you consider this category and take its Grothendieck group, and it also has a convolution product on it. So it also has a monoidal structure given by some sort of convolution. And this, what they prove is that this is isomorphic to the quantum enveloping algebra of the loop algebra of N. Okay. So maybe let me just say a bit words about the definition over here. So here, so x beta is a stack and the usual, like the way to define cotangent stack is the following. So we know that x beta is a quotient stack by this space of representations quotient by g beta. And then you get an action of g beta on the cotangent of this straight x beta. So this is just a vector space. This to each arrow you have a linear map between the corresponding vector space. So you have a symplectic action of g beta on t star x beta, and you get a moment map mu, which is from t star x beta to the Lie algebra of g beta dual. And here you still have action of g beta, which is on g beta star just by it's the coadjoint action, and you also have an action by dilation. Okay, so the C star action, it dilates elements in T star x beta by weight 1, and then dilates elements in G beta by weight 2. And mu is equivariant for this action. Okay, and then by definition, the cotangent stack T star of x beta is you need to take the derived fiber of, like we consider as a DG stack, and you take the derived fiber of 0 at for mu, so which is like T star beta beta star. So this is a derived fiber product, and then quotient by the action of this group G beta. And then when I put whenever I put a C here, it just means here I want to take the quotient by G beta cross C star. Yeah, I actually need the C star to get the grading. So the C star action in this side will correspond to the Q here. Okay. Maybe let me explain this in a concrete example, which is also an example I'll be interested in later. So this example is if you consider the case of SL2, then Q is just a point. And then in this case, there's no arrow, so x beta is 0, and so is T star x beta. And therefore, the moment map will just be, and yeah, I need to fix the dimension vector. So let's say, in this case, beta is just an integer. Let's say beta is r. Then mu is just so I'm considering 0, but with an action of GLR. So mu is just sending 0 to GLR dual. And then now if I consider this T star X beta, I'm just considering the self-intersection of 0 inside this vector space GLR dual. Okay. And then quotient by G beta plus C star. Okay, but as we know by taking the causal resolution, so this is nothing than just representation. This is the same as like GLR star, but you put it in degree 1, and then quotient by, here it's quotient by GLR. Okay. Okay. And then I want to consider the category of DG coherent sheaves on this category. And then in this example, it will just be nothing else than just a representation of the exterior algebra of GLR. And then I need to consider a modulus over this algebra, which is equivariant with respect to GLR cross C star action. Okay. And DG co. And therefore, when I consider the derived category, then by causal duality, so the exterior algebra is causal dual to the symmetric algebra. So then I'm just considering, yes, I think I forgot to do here. And so I'm just considering the modulus over the symmetric algebra, which are GLR cross C star equivariant. And so this is nothing else than the derived category. And then this is nothing else than just the derived category of coherent sheaves, which are GLR cross C star equivariant on the space on GLR dual. Okay, so this is the category which occurs in this theorem for the case of SL2. In the more general situation, this category will be more complicated, but in the case of SL2, this is kind of a familiar category people have studied. Okay. And so now this raised the following question. So you know that before what happened was that you consider constructible sheaves on X beta, and you have this lucid category, which is a nice category. And then you can describe it using quiver Hecke algebras, which is an algebraic description of this category. And we would hope to have a algebraic description of this coherent category so that we can better understand the categorification of loop algebras. But I think, well, this is too ambitious maybe for the moment. I think there's some work on this, but there's not a very good formulation of what we should do at the moment. But you can also, but there's another like question which you can formulate is the following. So so let's see. So if we consider Q, so here Q is the quiver is of finite type. And then we have considered its loop algebra of MQ, which is a subalgebra of GQ loop. But in this case, this is part of the Lie algebra, the affine Lie algebra of GQ. So in other words, here I have the Q hat, which is corresponding affine type quiver. And this is a Kac-Moody algebra. And therefore, here we also have a positive part, which we know how to categorify by quiver-Hecke algebras. And you can ask, so here you have a categorification by this coherent sheaves, and here you have categorification by quiver-Hecke algebras, and you can ask what's their relationship. Okay. But of course, like these two parts are not the same same algebra, but they have an intersection, which is basically NQ of T. Sorry, NQ of T. So now you can restrict both categorifications to the enveloping algebra of this subalgebra, and you can ask, are they the same categorification? So that's the question we pose, and it's also the question like we address in the case of SL2. So maybe I can put it as, so goal is compare coherent categorification of UQ T and categorification by quiver-Hecke algebras. Okay. Okay. So now, are there any questions? Okay. If not, I would go into the case of SL2. So this is where we can really say something. So in the case of SL2, the first thing you want to do is actually here, as I explained, if we look at this part, we're actually considering a sub-algebra inside UQ of NQ hat. So you want to first find, like, you want to say how to categorify this using quiver-Hecke algebras. And actually, it's for this purpose, it's more adapted to consider like the categorification of the quantum coordinate ring. In other words, it's more adapted to consider the category which is like modules, finite dimensional modules over quiver-Hecke algebras. You don't want to take projective modules, otherwise you need to consider complexes, etc. And so in our situation for SL2, what we do is that we consider, so in this case, the affine SL2 quiver will be just 2 vertices and 2 arrows. And actually here we need to, like, the choice of orientation is important for us. It's basically because, as Raphael explained last time, in this picture, actually, we see more, like we can also see what the dual PBW basis corresponds to. Okay, and the definition of dual PBW basis depends on the orientation of the quiver. And here, since we're considering a sub-algebra, like, what we want to do is to pick the generator, which are just some root vectors, and then consider the subcategory generated by those modules. Okay, so that is that is the idea of the subcategory. So now let me see. So yeah, so we consider the quiver where this arrow I will call the 0, and this arrow this vertex I call 0, and this one called 1. And then and then the SL2 quiver for me will correspond to the vertices indexed by 0. And then now, in other words, my NQ will be C of E0. And then in this case, I see that all the roots appears in NQ of T are of the form alpha 0 plus n delta for positive n. So this thing I will denote it by beta n. Okay. And then I fix, so consider fix a convex order so I can define the proper standard modules. So we fix some convex order on the all the positive roots for this Q hat in the following way, such that alpha 0 is smaller than alpha 0 plus delta and etc. And then all the imaginary roots are in the middle. And then for alpha 1, it's alpha 1 plus delta is smaller than alpha. It's smaller than alpha 1. Okay, and then given this convex order, you can and then for each well, you can define a dual PBW basis in this situation, but for the moment, actually, I don't. Yeah, and then you have so you have this dual PBW basis vector for each root vector beta n. And actually, in this case, it is an element in the dual canonical basis, so it corresponds to a unique simple module, simple R beta n module, which I denoted by L beta n. Okay. So this should be and later this should be a proper standard module. It corresponds to beta n, but it's all actually simple when I consider a root vector. And now the subcategory I'm interested in will just be the Serre subcategory generated by all the product of these beta n. Confused by my notation, L beta n. L. So I consider the sub-monoidal category inside the category of all the R beta n modules, graded finite dimensional modules, generated by this L beta n and all its shifts. So this is so it's closed under the monoidal structure. So this like monoidal Serre subcategory. And then by construction, the Grodienti group of this will correspond to this AQ of NT. So this will be the good candidate to compare to the coherent side. And then our main theorem is the following. Maybe let me first always hesitate on between these two. So maybe let me first put a main conjecture as it's more natural. So the main conjecture is that there should exist graded monoidal, an equivalence of graded, this equivalence of graded monoidal categories between, on one hand side, you just take the derived category of this category C I define here. Okay. And then on the other hand side, we take this coherent sheaves, which are GLR cross C star equivariant on GLR dual, and then take the sum over all the R's. And also here, I need to impose some some condition on the degree of the coherent sheaves. Because, well, this is a detail. Well, this is because on the coherent side, all the coherent categorify this thing, and now I want to take a subcategory. And so this is requiring the degree of the coherent sheaves to be positive. Actually, here I'm considering, you see, I'm considering some like GLR equivariant coherent sheaves. Like if I simplify for, if we consider just this, the tilting modules here, which is structure sheaves on this tensor product with a representation of GLR, then the condition here is that I'm taking the polynomial representations of GLR instead of all representations. So, so this is the conjecture. For the moment, we have some technical problem, or maybe it's not just technical, but we have some problem to prove this conjecture. But we can prove, what we can prove is the following result. So what we can prove is okay. What we can prove is the following. So we have an equivalence of graded triangulated categories between I take the homotopy category of projective modules in a modification of this category C. I will explain this modification. Well, maybe let me just say it right away. So this modification is the same. So it's a subcategory inside C. It has the same simple objects. So it has the same Grothendieck group, but the simple does not have same extensions. So it's not very far from this category. The only difference is that we have killed some central actions. Like here, I have a center, and a priori, this center action can be anything, but it's locally nilpotent. But here, I require the center action to be nilpotent, to be 0. So that's the difference between these two categories. And then killing this central action corresponds to restricting to the nilpotent cone on the coherent side. So so on the right hand side, what I get is I need to consider like derived category with perfect cohomology on coherent sheaves on the nilpotent cone, which are GLR cross C star equivariant. And then I also have some positive conditions on the degree of the sheaves. So we can prove this is equivalent. And we can also deduce an abelian equivalence from this. So this is first thing. And then the second thing is we deduce an equivalence of abelian categories between this C sharp and the perverse coherent sheaves. GLR cross C star equivariant on the nilpotent cone. And so this is very concrete. And so this equivalence, let me denote it by E hat, E sharp. So this was supposed to be E, and this is E sharp. And we can also match up the structures on both sides. For example, on the left-hand side, so we have learned last time from Raphael's talk, there is like Yeah, actually not sure if it's, but there's some like polynomial highest weight structure on the category of R modules. And if you consider like finite dimensional modules, it has a, so this category has a proper stratified structure. And where you have standard modules, you have proper standard modules and satisfy some axioms. And it was known that on the perverse coherent sheaves side, it also have a proper stratified structure. And actually, this equivalence is compatible with these structures on both sides. So we can check. You can actually we can compute image of proper standard modules under this equivalence. Okay, it's what you expect actually. And also as we want, so this E sharp on the Grothendieck group is just the identity map, because both sides categorify the quantum enveloping algebra of NQT. And then we hope to prove this is monoidal, but for the moment we can only check it on objects, so that we can prove it's weakly monoidal. Okay, so this is basically the result. Let's see. So how many time do I have?
I mean, maybe 20 more minutes.
20 more minutes.
I just wanted to just clarify once again. So the Grothendieck group or ring of this category is a AQ. It's what you wrote at the top.
Yes.
AQ and QT.
Yes, the Grothendieck ring is AQ of NQT.
I have some questions if we're pausing for questions.
Yes.
So you said that you could match up the proper standards on one side with something obvious with what you expect on the right hand side. What is it that you expect?
It's no, we know how to match up. So on this side, the proper standard module is given by this Anderson-Jensen sheaves.
Are those used to describe or?
Yeah, it's very concrete. It's let me think. So so here you consider the cotangent of GLR, the flag variety for GLR, and then you have the Springer map, and then on the other hand side you have the projection to the flag variety. And what you do is you just pull back a line bundle here, and then push forward back Q.
Got it. Okay, great.
Yes, and so you define O lambda like this. So this is called Anderson-Jensen sheaves. And then the proper standard modules are like certain Anderson-Jensen sheaves.
So from the combinatorial viewpoint, I mean, what's natural basis in the Grothendieck group of this category for a fixed R? Is it easy to describe?
This category?
Yeah.
So from a combinatory, like in this category, the simple objects is also some sort of IC sheaves.
But so you need to take choose an orbit and then lost some additional data, like some kind of representation.
It's parametrized by an orbit and a vector bundle on orbit.
And so it ends up to reducing to something like an orbit plus representation, irrep of a stabilizer of the point on an orbit.
Yes, exactly. Yes.
And then somehow you saying that C# and C had the same size, had the Grothendieck group of the same size.
Yes.
So somehow there is a principle saying that the size, when you reduce from the whole GL star to N star, there's no difference in the size of the Grothendieck group.
It does not change because I'm taking, yes,
It's like an even X thing, like all the X's are in even degrees, or is it like what happens in geometric Satake?
yes, it is like what happens in the geometric Satake. I think it's just because we're taking this C star action. It's equivariant with respect to C star action. And so here you don't when you go to GLR star, you don't get more objects, but you get more extensions between objects.
Well, thank you.
Yes.
Can I ask one more question?
Sure.
So what happens at the origin? So the perverse coherent sheaves supported at 0 should be like representations of GLR, graded representations of GLR.
Mm-hmm.
And those correspond to like what part of C#, or like this looks like a geometric Satake is hiding inside here somewhere.
Yes. Mm-mm.
I mean, it's a derived version of a geometric Satake. That's why it's less obvious to spot. So Bezo-Kamenikov-Finkelberg.
Right. I was just, it's really like kind of like the same thing, or just like that's the derived version of geometric Satake is what's happening at the origin. Is that the right statement?
It's a global thing, yeah. No, it's a global thing, yeah, the derived version of
Yeah, the derived version is just you describe the derived category of geo-equivalent sheaves on the
No, yeah, you're right. I'm being stupid. Yeah, of course. No, cool.
Okay. Well, I guess I can either explain the proof or explain some application to cluster algebras, but I don't know which way people prefer. I think maybe I don't have the. Maybe I can just say quickly the idea of the proof, but you will see it's very particular to this case of SL2. This equivalence. So what we do is to prove this equivalence, and then you can compare the image of some standard objects, which allows you to compare the heart. And to it, the top equivalence is established as following. So it's via a chain of, yes, I think I should. A chain of equivalence between triangulated categories. So you go first from this left category of quiver Hecke algebras to some homotopy category of semi-simple complexes on the affine Grassmannian, which is some thick version of affine Grassmannian. And then you need to go to the usual affine homotopy category of complexes on the usual affine Grassmannian. And there you use derived Satake to relate it back to perverse coherent sheaves. And I don't write all the details. And so it's interesting to maybe say what these equivalents are. So the first equivalence is actually related to this quiver. So we know that if you consider coherent sheaves on P1, it has a tilting generator, which is OP1 plus OP1 shifted by 1. And it's well known, its endomorphism algebra is just the path algebra of this quiver, of this Kronecker quiver I wrote at the beginning. And therefore, I have this derived equivalence induced by this tilting generator between the derived category of coherent sheaves and derived categories of representation of this quiver. And under this equivalence, you can match up here the part which are vector bundles on P1 of positive degree with those which are pre-projected representations of this okay. And then so and then you get an isomorphism of stacks between this vector bundles on P1 and isomorphism class of pre-projected representations. So let me denote this by Y, and this is a substack of our XQ at the beginning. So this is an open part inside X, and then it's well known that this bund P1 can be described as you take like K is the field of Laurent series and O is formal power series in Z, and this is by Weil renormalization theorem. No, uniformization theorem. This is the same as GK quotient by GO and quotient by G of O minus on the other hand side. So O minus is C of Z inverse. And therefore, just via this isomorphism of stacks, you can compare this. So you can compare this category C I was explaining before taking the sharp. This C projective is actually you restrict your IC sheaves from X to Y. So this is actually equivalent to semi-simple complexes on Y, and this is same as semi-simple complex on. So you interpret like this. So this is the thick, so-called the thick affine Grassmannian, and then the quotient on the right is the usual affine Grassmannian, and therefore you have choice here. You actually take complex which are GLO equivariant, GO equivariant on the thick affine Grassmannian. So this is the first equivalence. This just follows from this isomorphism of stacks, and then the equivalence C is just derived Satake. So here, and maybe I should write it better. So this is GO equivariant complexes on the thick affine Grassmannian, but this is also GO equivariant on the thin affine Grassmannian. And then like my point is the first equivalence and the last equivalence, I can do it both for the category C and C sharp. And where I cannot prove for C, but we can prove it for C. Yeah, so in the middle, the difference between C and C sharp is if I want to consider C, I should take GO equivariant sheaves. And if I want to consider C#, I only need to take GO constructible sheaves. And for the constructible case, we can provide an equivalence between these two categories using Radon transform. But for equivariant things, it's more complicated. And for the moment, we don't know how to explain, how to construct this equivalence. Okay. So that's, yeah, that's the idea of the proof. And then maybe at the last, I'll explain an application to cluster algebras. So the application is the following. So we know for any, so this is a theorem due to Geiss-Leclerc and Schroer, which says for any Kazhmoudi algebra G, and you take W in the while group, and then there is, so on the functions on this NW, so no, the function, yeah, function on NW, where NW is the unipotent group, which is the product of N alpha for alpha, which is a positive root intersection with W of negative. And they say this on this coordinate ring you have a cluster algebra structure. And if we want to consider AQ, we have a quantum cluster algebra structure. And then this thing has been categorified by, so the monoidal categorification of this quantum cluster algebra has studied by many people, and especially recently Kong, Kashiwara, O, and Kim and Park. In a series of works, they studied how to categorify this using quiver Hecke algebras. So, so monoidal categorification of AQ and W via quiver Hecke algebras. And it's similar as the category defined before. They study some standard representations for the quiver Hecke algebra. Like the standard modules plays an important role in this monoidal categorification. And then in the case of SL2 affine, if we consider we pick W to be the product of the two simple reflections to the power n, and then this phi plus intersection with W phi minus will be precisely this alpha 0 plus k delta for k positive and smaller equal to 2n minus 1. Okay, remember I was taking the part where just all these n's are positive. But here, if you take this element, you take a truncation of that part. But if you let n go to infinity, you get what I had before. And so if you take this, then there is another categorification, another monoidal categorification of the same algebra using a different category. So this is due to Curtis and Willems. And what they use is they also use a Affine-Grassmannian, and they use perverse coherent sheaves on the on the Affine-Grassmannian, but for this GL of this capital N, and they need to take they need to take the positive lattices inside the Affine-Grassmannian, and you consider GLO equivariant perverse coherent sheaves on the Affine-Grassmannian. And what they prove is that this also provides a monoidal categorification of the same cluster algebra. And then a natural question is to how to compare them. And what we use here is that there is a result by Finkelberg and Fujita, which constructed a map from the, so maybe let me just say it directly. They constructed a fully faithful functor from, oh, is it a free? No, sorry. They just constructed a T exact. They constructed graded monoidal T exact functor from this derived category of coherent sheaves on the nilpotent cone to derived coherent sheaves on these Van-Grassmannian. And here here the R means, yeah, maybe let me say it. So for GLN, the Van-Grassmannian parameterize all lattices in Kn, where L is O lattice. And this R part is just, you consider the lattices which sits inside the standard lattice and has codimension R. So and on this space you have so your Z will be a nilpotent operator, and this vector space is of dimension R. So you have a map from this to from this part to the nilpotent cone for GLR. So this was my and this functor is just given by pullback via this map. And then it matched the perverse coherent structure here and the perverse coherent structure here. And since our theorem gives you a functor, an equivalence from this quiver Hecke algebra modules to the perverse coherent sheaf on the nilpotent cone, you can compose it with this functor to produce. So you produce a functor from this C# category for this W truncation to perverse coherent sheaves on the Van-Grassmannian. Okay. And then we can prove that this is, so we can prove that this functor is faithful. So we have a graded monoidal faithful functor. Between these two categories. But for the moment, we don't know if it's full. We would hope it's full, and then it will say that these two categorifications of this cluster algebra is equivalent. But for the moment, this is not achieved yet. Okay, and I think that's all I want to say. Thank you.
Well, let's thank the speaker. Questions?
So is there any idea what you said that it was too bold to do at the moment, but maybe there were hints of it, like to figure out what an algebraic version of this category would be.
Well, I don't know. On one hand side, I would say that the equivalence of modules over quiver Hecke algebras give you some algebraic description. Well, you at least have an algebraic model for how to describe this category. But I think the naive hope of like finding a generator and compute the endomorphism of this generator is, like, for the moment, I don't know how to do this.
Am I already supposed to know how to think about these standard modules associated to the positive roots in affine type? I know how to think about simple is what I meant to say. I think I know how to think about standard modules, but I don't necessarily know how to think about the simples. Or is it just like really easy?
Simple modules for what?
These L betas that you had earlier. That generate the category. That generate the category C. I think you just went past it. Down low. I think you went too
this
far.
one.
Yeah, right around there.
Well, this is okay. So there are two descriptions of this kind of modules. So one, you can just say, in this situation, E beta n star is a dual root, is an element of the canonical basis. So you have a simple module corresponding to it. And the other way is to say you have, you can define them as some sort of cuspidal modules. You can define, so now you have an order and you can look at modules induced from a given order. And if you cannot obtain it from, and then it produces you some cuspidal modules, and this L beta n can define in this
with
way.
respect to this convex order?
With respect to this convex order, yes.
Huh. Okay, I don't know how to say. Cool, thanks.
Some more questions? So Ben wrote a question in chat.
Just for the crowd. It's not directly related, so.
Okay, wait, there's also a theorem describes them. Oh, okay. So yeah, so the for affine case, there's also some work by Peter McNamara on this standard modules. The thing is that you can the affine case is complicated basically because of the imaginary roots. So for the imaginary root part, like, the root spaces are not dimension 1, and it's complicated. But the moral here is that if you only consider real roots, like on the one side of the for this, you see, for this convex order you fix, you actually parted your real roots into two parts. And if you only stay with one of the parts, and then the geometry of the representation quivers behaves as a finite case.
Gotcha. Thank you.
So let me stop the recording.
Mhm.